I see our first guest speaker has arrived. Amazing like science fiction to most of us, but groundbreaking research in regenerative medicine is going on right down the road from us at Wake Forest University Baptist Medical Center in the Institute of Regenerative Medicine. Our speaker, Dr. Tony Atala, a recognized pioneer in the area of regenerative medicine and a practicing surgeon, is the director of the Institute. He leads a group of scientists who were the first in the world to successfully implant a laboratory-grown organ in humans. His work was listed as the #1 science story of the year in the field of medicine by Discover magazine. Today, his team is working to grow 22 different organs and tissues in the lab. He and his team will change the way we live and change the way we work. So Dr. Atala brings a unique perspective to the job opportunities that will develop in the medical field. Dr. Atala, thank you for joining us this evening.
Thank you so much. Just wanted to share with you some of the work that we're doing at the Institute, and it's great to be with you tonight for this great initiative that you're having here at Davie County. Basically, what I'd like to do is really give you an overview of just a glimpse of some of the work that's going on at the Institute for Regenerative Medicine at Wake Forest. If we could have the next slide, please. Basically, our mission at the Institute is to improve lives, patients' lives, by developing these regenerative medicine technologies. So what is regenerative medicine? What is it that we're trying to do? Next slide, please. Actually, what we are trying to do is really to bring the power of your own body to heal damaged tissues and organs. And we do that by using very simple techniques that actually put together are quite complex, but simple units that you can put together by taking small pieces of tissue from the body, less than half the size of a postage stamp. You then take that tissue and you take cells from that tissue and you grow those cells outside the body in large quantities. And then you start layering those cells into three-dimensional molds, scaffolds if you will. It's very much like baking a layer cake. You take the cells and you do it one layer at a time. And what we're doing right here is actually creating a digit by using the patient's own cells on this three-dimensional mold. I'll show you one more example of this. And next slide, please. You're going to see here this organ. So let's say that you want to create an organ and you have this patient that walks in to our medical center. One of the things that we could do potentially is take a very small piece of that patient's organ, again, less than half the size of a postage stamp. And that's what we're doing here with this organ called the bladder. And we then take that small piece of tissue and again, we tease it apart. And that tissue is composed of two different cell types. And we then grow and expand those two different cell types outside the body in large quantities. And then we use this three-dimensional mold in the shape of the organ. And we then paint one cell type on the outside. We paint another cell type on the inside. Again, you can make the analogy, you're making a peanut butter and jelly sandwich, right? You're just taking different cells and put them on this three-dimensional scaffold, which is like the bread. You then place it in an oven-like device. It has the same conditions as a human body, 37 degrees centigrade, 99% oxygen, 5% CO2, and then you actually put it in an oven-like device, and the whole process takes about 6 weeks. From the time you take a small piece of tissue to the time that you have the organ ready to be implanted. This is what's been done now in some patients. Next slide, please. So right now at the Institute, we're working on many different tissue types. We're trying to engineer heart valves, blood vessels, liver, muscle, skin, things that can go towards treating patients for many different conditions. Some of these are already in patients, like the bladders or cartilage or urethras, which is a channel that connects the bladder to the outside of the body, muscle that we put into patients, but some of them are still in the developmental stage, such as the liver, for example, or more complex organs, such as the heart. Very complex. It's going to take years to get there. Next slide, please. This is actually an engineered heart valve. And what you see here is that's the heart valve in a bioreactor that's actually maturing the heart valve so that we can get it ready to implant it. So again, same technology. You take cells from the patient, grow the cells outside the body, place them on this three-dimensional mold, the cells create the new tissue, and the mold will go away. It will disintegrate over time. Next slide, please. This is actually a blood vessel bioreactor, and it shows that the blood vessel can actually pump, and you can actually see the blood vessel pumping away once it's mature. Next slide, please. And this is actually a muscle tissue that's being exercised. This is actually an engineered piece of muscle. Same strategy. We take a small piece of a patient's muscle, we place it on a scaffold, we then create the muscle tissue totally new. We start out with the cells, and again, 6 to 8 weeks later, we have a piece of muscle we've engineered by placing the cells on this three-dimensional mold in the same conditions as a human body, and then 6 to 8 weeks later, you have your piece of muscle. However, you just can't take that piece of muscle right away and put it to the patient. You actually have to exercise it. You have to exercise that muscle and prepare it so it's ready to do what it's supposed to do in your very own body. So let's say that you come in with an injury to your muscle and we want to make that muscle. We would take a small piece of tissue from your muscle, take about 4 weeks to grow the cells, another 2 weeks to place the cells in this mold, and then another couple of weeks to exercise it. And this very interesting thing happens if you don't exercise the muscle early on. You have to exercise that muscle from the moment that you're creating it. And if you don't exercise it from early on, it just won't work very well. You have to exercise that muscle from the time that you create it so that your body can recognize it as your own muscle. Well, guess what? That exercising of the muscle that you see on this slide is very similar to the exercising of our minds. And this program, STEM, this STEM program that allows us to really go after science, technology, engineering, and math, is essential for the types of things that not only we are doing, but many people are doing throughout the country and throughout the world in this field that we call regenerative medicine. So it's an interesting analogy. You have to start children early. You have to start them young. Because if you don't start them with these sciences early, they're not going to do as well. Just like this piece of muscle. And so this program is so important because it does allow for our students to really come to the forefront of where we need to be. We at the Institute are working on technologies that will lead to businesses in the future. And I was asked to mention some of the things that we could do with these technologies in terms of startups and companies that would actually provide these technologies. Not just us, but many other investigators at the medical center and throughout the biotechnology park are working on technologies that can really lead to the future. Businesses such as cell therapy, engineering tissues, engineering organs, devices to deliver cells, biomaterials, biotechnology. Really, the possibilities are endless. And to create such a structure, we need a workforce. And we need many types of scientists, whether they be molecular biologists, cell biologists, biomaterial scientists, mechanical engineers, physicians, all working together to bring these technologies from the bench to the bedside. So it takes all of us to bring these technologies forward. And programs such as STEM and the STEM Coalition are going to be critical for the future, not just of our community, but of our children's future. Thank you very much.